Valence bond theory. Here this theory is used to explain the formation of hydrogen molecule. Let the two hydrogen atoms be initially far apart from each other. Let the hydrogen atoms be denoted as A and B. The electron associated with hydrogen atom A is denoted as Ea, and the electron associated with hydrogen atom B is taken as Eb. The nucleus of hydrogen atom A is taken as Na, and the nucleus of hydrogen atom B is taken as Nb. When the two hydrogen atoms are far apart from each other, there is no interaction. But when the two hydrogen atoms approach each other, there will be new attractive forces and repulsive forces. There will be attractive force between nucleus and its own electron, that is NaEa attraction and NbEb attraction. There will also be new attractive forces, which is between the nucleus of one atom and the electron of the other atom, that is NaEb and NbEa attraction. Repulsive forces will also be there. The two electrons will repel each other. The two nuclei will also repel each other, that is EaEb repulsion and NaNb repulsion. Attractive forces tend to bring the two hydrogen atoms closer towards each other, whereas the repulsive forces tend to push them apart. But it is experimentally found that the attractive force is more than the repulsive force, and there will be lowering of potential energy when the two atoms approach each other. Ultimately or finally, a stage is reached when the attractive force is balanced by the repulsive force, and at this stage there will be maximum lowering of potential energy. At this stage, a bond will be formed between the two hydrogen atoms. The distance between the two hydrogen atoms at this stage is found to be 74 picometer. So when the two hydrogen atoms are at a distance of 74 picometer, there will be maximum lowering of potential energy and molecule of hydrogen will be formed. Overlapping of atomic orbitals. Consider the atomic orbitals s, px, py and pz. There are three types of overlap of atomic orbitals: positive overlap, which results in bond formation; negative overlap; and zero overlap, which will not result in bond formation. S orbital is spherically symmetrical and it has a positive sign. A p orbital has two lobes, and one of the lobes has a positive sign and the other lobe has a negative sign. Now consider the two pz orbitals overlapping with each other. Let the two p orbitals be taken as pz. The pz orbitals will overlap and result in bond formation only if the sign on the lobes of the overlapping pz orbitals is the same. If one lobe is positive and the other lobe is negative, then it is taken as negative overlap and the bond will not be formed. Consider overlap of a pz orbital and s orbital. Positive overlap will take place if the sign of both the overlapping lobes is positive. If it is negative, then it is taken as negative overlap. Next, consider two px orbitals overlapping with each other. If the sign on the lobes of overlapping px orbitals is the same, then it is positive overlap. If one is positive and the other is negative, it is considered as negative overlap. Similar is the case of two py overlapping orbitals. A px orbital and s orbital cannot overlap with each other. It is zero overlap. Similarly, a px orbital and py orbital cannot overlap with each other.